So, what does it mean for a chemical reaction or any process to be spontaneous? Well, in chemistry, for a chemical reaction to be spontaneous, it means that the reaction is self sustaining without any input of energy. The reaction causes the system that we're looking at to move from a less stable to a more stable state. And that process, that reaction, releases some form of usable energy to the surroundings. So there's a release of useful energy to the surroundings. Let me clarify a few things that I've just said. Activation energy. So we know that activation energy is the minimum amount of energy required for a reaction to take place. So spontaneous reactions, even though they have a net release of energy to the surroundings and don't require an input of energy to continue, they do sometimes require an input of energy to begin. Because there is an activation energy. So examples include that for methane to combust and create carbon dioxide and water, that is a spontaneous reaction. And once that reaction is going, like with a Bunsen burner or on your stove, that reaction will continue on its own. The heat produced in the reaction can sustain the breaking of more bonds and can keep the reaction going. But it still requires an initial spark of some kind in order to provide that initial energy to get it going. Another example is the combustion of diamond. Diamond is just an allotrope of carbon, a different form of carbon. And you can burn diamond, you can combust it in the same way that you could combust a piece of coal. However, the activation energy to do this is so high that it never really takes place, or we never really observe this happening. Another thing I want to distinguish is that spontaneity is also not the same thing as reaction rate. There are plenty of spontaneous reactions that are very, very slow. For example, like rusting of iron or the oxidation of iron, that process can take place over days, months, years. So it's not a quick chemical reaction. However, it does lead to a more stable state, and it is considered a spontaneous chemical change. Another like sort of reverse example is that when we do electrolysis of salty water and we produce gases, you can produce those gases very quickly, even though electrolysis is a non-spontaneous process that requires the input of electrical energy. So just a couple of examples to point out that spontaneity and reaction rate are not the same thing. Finally, enthalpy change. Enthalpy change, or delta H, we've looked at exo and endothermic reactions releasing and absorbing heat energy. Enthalpy change is very closely linked with whether or not a process is spontaneous, but it is not the only thing that we need to consider when we decide if overall process is spontaneous. So exothermic reactions are more likely to be spontaneous because there is a release of heat energy, which is very closely related to a release of useful energy. However, there's more to consider. So I've got a couple of spontaneous processes happening on this page, and we're going to try to see what they have in common. So if you have a pumpkin, and you have your nicely carved pumpkin here, highly complex structure, right? A pumpkin has many complex molecules, proteins and lipids and carbohydrates and DNA, billions of atoms all connected, millions of atoms at least in those molecules, all connected in highly specific, highly ordered ways. But what changes occur to the pumpkin after you remove it from its plant stem and you carve your crazy shape here, and then you let it sit out? Well, over time, the pumpkin decomposes. And those highly complex molecules, those highly organized molecules of DNA and protein and fat, they slowly break down over time. And eventually you're left with, well, in this picture, basically a pile of slop. Well, what's really happened is that you've gone from highly complex molecules to simpler molecules, right? And the molecules are simpler, but you have many more simple molecules than you do of those highly complex molecules. So you've gone from relatively few highly complex molecules into many, many simpler molecules. And now in that process, there's probably also been a release of chemical energy. So there's probably been some heat released. So those are the different processes that have happened. We've taken these highly organized, highly complex molecules, and we've broken them down into simpler molecules, releasing energy along the way. Now, that's a spontaneous process. If you leave a pumpkin out, it will eventually turn into this pile of simpler, sloppy molecules. It basically return to being dirt. Is the reverse process spontaneous? Well, no. Obviously pumpkins grow, but pumpkins only grow with an input of energy. And that imprint of energy for a pumpkin is solar energy. Without solar energy, the plant won't be able to grow. And the plant has to take very simple molecules like carbon dioxide and water and put them together into very complex forms like carbohydrates and proteins. Um, so the reverse process of a spontaneous process is not spontaneous, and it requires an input of energy. So we need an input of energy to go from many simple molecules to fewer highly complex molecules. So there's something about spontaneity that has to do with how simple the structures are, how organized they are, and also how many structures there are. So going from something that is highly complex and breaking that down into many, many simpler things is more likely to happen than to take many, many simple things and put them together into fewer highly complex structures. We can see some other examples of that here. These don't involve any chemical reactions. These are just physical processes. If I was to have two gases, for example, nitrogen and oxygen, two pretty unreactive gases that don't react with each other at room temperature, if I were to separate them, I have them in these two separate containers, and then I open the valve between them, we know that the gases would mix. So how does the system change when the valve is opened? Well, at the beginning, I had a very highly ordered system. Two gases, and they're separated. And I've got two pure gases. And we know that if we open the valve, then the gases mix. So when given the opportunity, two gases mix completely. They spread themselves out evenly. Would the reverse process ever happen spontaneously? Would those two gases separate back out into nitrogen and oxygen all on their own? No, of course not. That would never happen. The probability of all oxygen atoms on one, or molecules on one side and nitrogen molecules on the other side is just so unlikely that it's never going to happen. So reverse would never happen. So again, if we think about how does this compare to the previous one, at the beginning we have a highly organized system. We have one gas on the left, one gas on the right, and they're separated. And then given the chance, those gases will mix and become more complicated. They'll become more disordered as they spread out between each other, and they will never do the reverse thing on their own. We'd have to do a lot of work to separate those two gases out. One more example. If I add a drop of food coloring to water, that food coloring is like the solute, and we know that as we let that drop mix, it's going to spread out until the concentration of the food coloring, the solute, is even throughout the water. And that reverse process will never take place. So again, it's sort of like the gas example. At the beginning, you've got the food coloring and water are separated. We have these two pure samples, so it's sort of a highly organized system. And over time, the two substances will mix, and it's less organized. And the only way to get the food coloring back out would essentially be to evaporate off all the water, and that would require a big input of energy, a big input of work in order to separate these things back out into a highly organized system. So what do they all have in common? All these spontaneous processes basically have in common that we're going from more organized, more ordered systems to less organized systems over time. That seems to be spontaneous. So we're going from highly complex biochemical molecules to simpler molecules. We're going from two separated pure gases to mixed gases. We're going from separated solute and solvent to perfectly spread out solute and solvent. This seems to be the way of the universe. This is the way things happen, and the reverse processes don't happen unless we do a lot of work. This concept is known in science as entropy. Entropy is the measure of disorder of a system, or in other words, it's the measure of unusable energy. The more unorganized things get, the less likely they are able to do useful work for you. The overall entropy or disorder of the universe is always increasing. This is not word for word, but basically the concept of the second law of thermodynamics. The first law of thermodynamics is the law of conservation of energy, that the total amount of energy in the universe stays constant. We don't lose or destroy or create energy. All the energy is here. However, over time, the amount of energy that is usable is always going down because the universe is always leading to more and more and more disorder and less useful stuff. Right? So now, if we go back to what we saw, right, all the previous examples involved increases in disorder, increases in entropy. Okay, so if you have a gas that's spread into one corner, over time, you know that that gas would naturally spread out to be spread out all over the container. And the gas particles would never do the reverse. They would never all end up in the corner and stay there. The probability of that happening is extremely low. And so as we go from a highly organized system where they're all stuck together to spreading out, the particles have become more disorganized. When bricks fall off a lorry, as it says here, that when they fall off a truck, you know, just by your intuition, by your experience, that the bricks are not going to fall into a neatly organized pile or a pyramid, right? They're naturally going to fall into a chaotic disorder, right? So the natural way of things is for order to fall apart into more disorder. That is just how the universe works. When we look at entropy in our class, we're always going to be looking at a system, not the entire universe. So for the universe, delta S, or the entropy change, is always increasing, is always a positive value. But for the given process that we look at, the change in entropy can be either positive or negative. If there's more disorder after something happens, then we say that the entropy has increased, and we get a positive value of delta S. So S is the symbol for entropy. If the entropy decreases and we get more order in the system, then we say delta S is negative. So how do we qualitatively assess things? Well, one key thing to look for is a change of state. The solid state is by far the most ordered of the states because the particles are in fixed positions. As solids become liquid, they increase their entropy. They become more disordered. As solids dissolve into water, they become more disordered. And as liquids and solids become gases, they become really, really disordered. The gas phase has by far the most disorder of any of the phases because the particles are highly spread out and they're moving around sort of randomly. So the gas phase is the most disordered of the states of matter by far. So there's a pretty common type of paper one question where they have you assess various chemical reactions and pick the one that has the largest increase in entropy, the largest increase in disorder. And so what you're looking for is which one produces gas. And also, the other thing you're looking for is which one makes more particles. So really what you're looking for is which one makes the most gas. The most gas created will equal the biggest increase in entropy. Let's check out these examples. A couple of things that are spontaneous, and then we could try to explain why they happen now. So water evaporates spontaneously. We know that it happens from any temperature from 0 degrees Celsius up to 100 degrees Celsius. Water will be converting from liquid phase to gas phase. If you think about this from an enthalpy perspective, it doesn't really make any sense. Water evaporating is endothermic. The particles, in order to go from liquid to gas, that is endothermic. That means heat is absorbed. So from an enthalpy standpoint, we would think that doesn't really make much sense. We're going to a place of higher potential energy in the gas phase. But we do know that this happens spontaneously. So how can we explain it? Well, the gas phase is far more disordered than the liquid phase. And so by going from liquid to gas, we've increased the entropy of the system, and therefore that can help us explain why this process might have happened. We know that the universe tends to go towards more disorder or more entropy. And so even though it's an endothermic process, there's such an increase in disorder that this still ends up being the more likely thing to happen. So increasing the entropy of the system can make this spontaneous, okay? For a chemical reaction, if you look at this one, this is where we're going to mix two solids. I have barium hydroxide. It's a hydrated compound. Barium hydroxide plus ammonium thiocyanate, and I stir these two solids together, and it gets really, really cold. It's a really highly endothermic reaction. So why would that take place? Why would these reactants just absorb more chemical energy and go to a less stable, weaker bonded structures? It doesn't really make sense from an enthalpy standpoint. However, if you look at the products, we've got lots more gas, right? We didn't have any gas on the left. We just had two solids. We had 3 moles total on the left. Got 1 barium hydroxide. I've got 2 ammonium thiocyanates on the left. And when I go to the right, I've got 1 mole of solid, but now I've got 10 moles of water, and I've got 2 moles of gas. So I've created way more moles of particles. More particles means more disorder. Let me do this someplace else, because this is going to take me forever. All right, let's just do it like this. So created more particles and row particles, and created more gas particles. Those are the 2 really key things that we've done in this reaction, and that means we've created a huge amount more entropy, and that can explain why this is spontaneous. Last thing to consider here with entropy is that actually you can calculate the delta S for a given reaction, and you will very likely be asked to do this on the IB exam. Absolute entropy values, so the entropy of a substance, actually can be measured, and they are listed in the data booklet in table 12. Looks like this. So you've got here delta H of formation values. We've got delta G of formation values, which we'll talk about in a little bit in the next video, and we've got entropy values. So for methane, when it forms from its elements, we get out negative 74 kilojoules for every mole of methane formed. Now, this is not a delta S value, and it's not a formation value. This is just the value for methane. How much disorder does 1 mole of methane have? It has 186 joules per degree or per Kelvin per mole of methane. It's kind of a hard concept to understand. But it is measured. They look at how much disorder changes for a substance from 0 Kelvin, where there is theoretically no disorder because all motion has stopped, till we go out to room temperature, or 298 Kelvin. That's how the entropy value is actually determined and measured. You don't really have to be able to define that value, but you do need to know how to work with it. So these entropy values, these S values, are not formation values. And so elements can have entropy values, even though they don't have enthalpy of formation values. That was one of the things we pointed out previously. I think when you see this in practice, it's easier than it sounds from my video description of it. You use table 12, and to find the delta S for a given reaction, all you have to do is add up all the entropy values of the products and subtract out all the entropy values of the reactants. You do have to take into account their coefficients. If there's 2 of something used, 2 moles of something used in a reaction, then you have to multiply that entropy value by that coefficient. But it ends up being pretty straightforward. Not all substances are going to be listed in table 12. And so if it's not in table 12, then it's going to be given to you in a particular question. So in this example, the products are chloromethane and hydrogen chloride, or hydrochloric acid. So I would look in this data booklet, and I find chloromethane here has an S value of positive 235. Let's write 235. And I'm going to look up hydrogen chloride, which is at the bottom, has a value of positive 186.9. So those are the S values of my products. And then I need to subtract out the values of my reactants. So I'm going to look up methane. We said methane was 186. And here given to me is the absolute entropy of chlorine, the element, as 223. And so if I add these together, I'll get the delta S. Let's see if we can do this quickly. So if we do the math out, the entropy change or entropy values of the products is 421.9. That of the reactants is 409, and so the value has gone up. It's gone up from 409 up to 421.9. That's a change of 12.9 entropy change, joules per Kelvin per mole. That change is positive, which implies that there has been an increase in entropy, an increase in disorder. Now that's a pretty small entropy change, and if we look at it, we should be able to get a sense of whether or not that makes sense. On the left, I have 2 moles of gas, one of methane, one of chlorine. And on the right, I have 2 moles of gas, one of chloromethane and one of hydrogen chloride. So the entropy change has increased, but it's been a pretty small increase in entropy. And that's because I had 2 moles of gas making 2 moles of gas. So on your own, it would be pretty hard to predict if this entropy change would be positive or negative. The only thing you could predict is that because it's 2 moles of gas to 2 moles of gas, whatever the change is, it's going to be pretty small, whether or not it's positive or negative. In this case, it was positive, so we've slightly increased the disorder of this system. So entropy is disorder. We can qualitatively assess entropy changes, and we can quantitatively calculate entropy changes using table 12. And the way of the universe is for things to become more disordered over time. Things that lead to more entropy are more likely to be spontaneous.